Hello everyone and welcome to the Advanced Large-Scale Fluid Effects in Houdini Part 1. My name is Tinka, and in this lesson I would like to give you a quick overview of the project file, and I'll mention where you can find all the necessary files, and also we'll go over the setup or the machine or my specs of my computer which I'm running, and all the technical stuff regarding that. So I think we can start. So in Chapter 2, we'll start by creating this entire section here by preparing our ocean and creating all the necessary attributes and the spectrum and so on. In Chapter 3, we'll start preparing our mesh for simulating. So this entire part here, also with this part here, is going to be dedicated in Chapter 3, and we're going to be preparing our animation and also converting it into a ocean guided layer and all the volumes we'll need in the flip simulation. Then the entire Chapter 4 will be dedicated to the flip simulation itself, compressing it, and of course then converting it into a water mesh, and of course down the line we'll add additional detail to it. Then the Chapter 5 will be dedicated to creating the source, all the necessary volumes we'll need in our whitewater simulation, and of course the whitewater simulation with the compression. And also in Chapter 5, I forgot to mention we're going to import our whitewater, do some adjustments or add additional detail, and prepare it for rendering. In Chapter 6, we'll dive into our ocean foam. So this entire section will be regarding our source. So we'll go over that in Chapter 6. Also, we'll create our volumes for our whitewater sim or our foam sim. Of course, we'll go through the solver and the compression and the preparing for rendering. Then in Chapter 7, we'll go over creating the spray. And of course the simulation itself here, which is going to be of course a pyro simulation. I added here a additional setup which I won't be explaining, but I think it's pretty interesting. It adds a lot of additional detail. Unfortunately, I didn't like it in my simulation, so I at the end didn't use it, but you can check it out. It's like a bonus. Of course, compressing it and then preparing it for rendering. And of course, in Chapter 7, we'll also go over the creation of the bird. So we'll create a particle simulation. Then we'll prepare our bird geometry or our FBX file, which you can find in the assets folder, or you should be provided with the animation of the bird, or you can use your own animation. Here we're going to be adding some different variation and then copying those birds into the points. And last thing I would like to mention is the camera. I'll have a dedicated video in Chapter 1 explaining how I did the animation. I won't go step by step, but I'll explain you the way I did it. At the end of the day, I'm not really that good at creating camera animations or anything like that. And then I would like to dive into the top network. So this top network I'll show you throughout the tutorial how to set up, for example, a basic rough fetch output, what wait for all does, and for example, creating the wedges, and I don't know, adding attributes to your wedges, and how to set up a simulation with multiple wedges. But I won't be recreating this entire setup because I think there's a lot of repetitive stuff and it's not necessary for the tutorial. But this here is for you to comfortably cache all the necessary files you'll need here. Of course, keep in mind that the file caches in the simulation are pretty heavy, some of them, especially the flip simulation and the water simulation. So I would like to talk more about the specs of my computer. So I'm going to show the specs I have here. So I am running a Ryzen 9 7950X, which is a 16-core CPU, which isn't that important. But the most important thing I would say is the RAM. So if you have 96 gigabytes, you should be able to recreate the same thing I did. With less RAM, I highly doubt that. You would need to lower some of the simulation's resolution. And if you have a computer which has sub 48 gigabytes, I created a preview, or in the flip simulation, I created a second version which had the twice amount, or the particle separation was twice as large, and the same thing I did in the whitewater simulation, so you can see roughly how the results should look. So yeah, and if you have more than 96 gigabytes, you should have no issues with that. I would like to also mention is that I'm using a Radeon GPU, but the main thing is in the attribute blur, you'll need at least 16 gigabytes if you're running the same simulation as I did. Because what happens here in the attribute blur, as we import our whitewater, I wanted to add some additional detail by using the attribute blur. And the attribute blur runs on OpenCL. So of course, if you run out of the dedicated GPU memory, the OpenCL will give you an error. So just to keep that in mind. Of course, I don't think anywhere else I needed that much dedicated GPU memory, maybe just in the viewport. And yeah, I think the file sizes, if you followed with the same resolutions, were pretty big. The whitewater was around 800 or like over 800 gigabytes. The flip was like 340. So I think next time I would lower these a bit, but the project is already finished and I think it doesn't change a lot. So yeah, I think this is everything regarding the technical part, but I would like to show you one setting which I haven't changed till like chapter 5 and I had a lot of crashes, is go into the preferences here, 3D viewports, and I already changed it, but on default you should have in Houdini 20.5 the render is set to Vulkan. I find Vulkan very unstable. Like I was getting crashes every 5 minutes, and it wasn't necessarily that I have a lot. I was getting crashes when I had a lot of particles in my scene, but I was just getting randomly crashes where I had nothing in the scene. It was just pretty terrible. So yeah, and OpenGL feels pretty well. Like I get very rarely any crashes. So yeah, I highly recommend changing this to OpenGL. By the way, if you change this, you should need to restart your Houdini. So yeah, keep that in mind. And yep, I think this should be everything regarding the lesson or regarding the introduction. And yep, I'll see you in the next lesson. Bye. Welcome to our second chapter. In this chapter, we'll create the basic geometry for our ocean, also prepare it for rendering and create all the necessary attributes. The only thing we'll need is the camera animation, which you should have from the previous chapter, or you can open the example files from the chapter 1 and continue from there. So let's start with the geometry node and call it ocean. Create a grid and this grid should be something like 4,200 by 6,500. 1250 and minus 320. As you can see, our primitives are not square shaped. And you can also see we have more resolution in this axis than we have in this axis. The reason, or the way we can fix this is by copying this, dividing it with a number you decide. I decided 50. Copy this, paste, copy, paste relative, and divide by 50 again. Now we can see that we actually have squared shaped primitives, which means we have evenly spread our resolution through our grid. Try divide this, probably like 5 times, should be good. And now I want to remove all the points that are not going to be visible in the camera view. So let's start by creating a box. Let me zoom in. So we have a basic box here. And we would like to create a wrangle, and I'm going to use a function called from NDC. So we want to get the position and use a function from NDC. NDC coordinates are actually normalized devised coordinates, and they're coordinates which are used to map three-dimensional position into two-dimensional space. The first input, or the first parameter, is going to be our camera direction, because we want to map or get the normalized device coordinates of the camera. So we know our camera lives in OBJ and it's called render cam. So /obj/render cam, and we want to get the position. Now, as you can see, something actually, let me make it bigger for like 7,000. Our box changed. We want to set this to 0.5, and copy this parameter and push it backwards. So minus by half of its size. And now you can actually see we have a geometry that represents the basic shape, or represents the camera view. We want to trail this. 320 should be good since we have 390 frames, so I'll put 320 so we're safe. We want to time shift the last frame so we get the entire sequence, and we're going to create VDB for polygons, which 25 should be good. We have something around 1.5 million voxels, and let me just make sure. Yeah, our grid should be fine. And let's use a create group node. We want to run it on points, call it in cam, enable bounding regions, and set the bounding volume. Now, if I did it correctly, we should have some points in our in-cam group. Now we can do a blast. In-cam, and delete non-selected. The next thing I want to do is measure the distance from our camera to our to each point on this grid. So we can do that from a node called distance from geometry. Sorry, wrong one. Distance from geometry. The first input is going to be our grid. The second one is going to be a geometry. So I'm going to use a object merge, and I'm going to import my camera origin. So copy the directory, place it here. We want to trail it the same way we did in the camera view setup. Again, 320 times. I'm going to zoom in so I can show you. This is the camera, as you can see. And we want to time shift this on the last frame, and we want to connect all the points. We can do that by creating an add, which is going to connect it by group, which connects it actually based on the point number. As you can see, it goes. The next part, or the next thing, I'm gonna plug this in. Sorry, plug this in, and we're actually going to get, I'm going to show you the distance attribute, sorry, geometry spreadsheet. Geometry spreadsheet, and here we have a dist attribute. The next thing we're going to do is we're going to promote this to a primitive attribute, because if we don't, I'll show you what would happen. Split, for example, dist smaller than 2500 points, and then merge them back. So the reason why I'm doing this is because, first of all, I want to try divide it afterwards, and the try divide requires a primitive attribute for it to work. You can't put a point attribute and expect it to try divide. So here we get this line. The reason for that is because we're splitting it based on points. So for example, this point here belongs to this group, but this primitive requires this point to exist. But since this group, our further group, doesn't have this point, it's going to delete this primitive. You can fix this by promoting it to primitives. That way, the primitive doesn't, you're determining the distance based on primitives, not based on points. So let's create an attribute promote. Dist into primitive. The next thing I want to do is blast based on dist smaller than 6000 and primitives. The reason I'm doing this is because in Houdini, the ocean is always perfectly flat, but in reality, the curvature of Earth will create a slight dent in the distance. So you can create a curved edge of your ocean to simulate the curvature of Earth. It's a small detail, but it will actually help to look a bit more realistic. And it doesn't actually cost you anything. So the next thing I want to do is I want to try divide the geometry closer to the camera we get more resolution, and the further we get less resolution. So the way we're gonna do it is by try divide. So the first, I'm gonna use distance attribute again. Smaller than 2000 will be try divide once. And as you can see, let me see where I can find it. Here. It try divided up until 2000, and after there was no try dividing happening. I'm going to do this like 5 times. Sorry. So copy this, I'll set this to manual. This one is going to be 1250, then 500, or let's do 750. Next one, let's do 450. And the next one, let's do, I don't know, 125. Now if I load this again, we'll get a mesh that's has more resolution near the camera than further away from the camera. The next thing I want to do is, since I need this distance attribute, but I don't need actually the in cam group because it's useless, because all the points are actually in the cam group. We can use a clean. And also the reason why I'm using a clean and, for example, not a group delete is because clean also deletes points based on this the generacy tolerance that are not connected. So just in case if there are points somewhere around flying, this will remove them. So remove group points. And let's use a file cache. So I want this to be a node name. So let's call this ocean grid. We know it's not a simulation and neither time dependent. And we can save this to disk. So this will be the end of the lesson, and I'll see you in the next one. Bye. So welcome to our second lesson of chapter 2. In this lesson, we'll create the ocean spectrum. But before that, I'm going to correct my mistake from last lesson. As you can see, our grid is actually not being in our camera view. That's due to the fact that I miswritten or mistyped the scale. So change this from 6,500 to 7,000 and this to 3,000 or minus 3,000. Also, additional thing which I forgot is in the group create, I didn't add any isosurface offset, which led to actually blasting points that are actually in the view. So we're gonna set this to like 20 to actually fix this. And save this back to disk. Save this to disk. I apologize for that. So we can begin. So we're going to take our original grid, scatter some points on top, and we're going to use the density scale. The reason for that is because density is much more reliable. It's determined by actual scale. So the density always stays the same. The total count is not useful, since if I change my grid size, I still get the same amount of points, which means I actually get a different density of points. And in creating oceans, it's good to have consistency in your point density. The next part, we're going to split this because we want to merge two ocean spectrums, so it doesn't look obvious that there are repeating, or that the ocean spectrum is repeating. So we're going to use a function that I'm going to copy and explain what it does. It's this one. You also use it in the oceans presets for large oceans, and I think everywhere else except for the small ocean. And I'll explain what the function does. So the up input path is a function that retrieves the input. The dot means it's retrieving the input of this node. If I, for example, set a, I don't know, a null, copied the directory, now it would be retrieving the input of this one. As you can actually see, it's actually still working if I plug this in. But let's keep it on 0, so it's this, and or the dot, and the 0 means it's the first input. The endpoints is a function that retrieves the point number. In this case, it's 4,440. We can actually check that also, which is true. By clicking this, from 0 to 4,400 means that we're split, that all the points, I'll show you. Let me copy this. So points ranging with point numbers from 0 to 4,440 are going to be in the first group. And since we have no points left, there's nothing that can be in the second group. Sorry. See? But if we add dot 2 or double dot 2, we say that every second point number or every second number is going to be in the second output. So we get the same result as here. But the reason why we actually use the expression is for it to be consistent and procedural. So that's about that. Now we want to create our ocean spectrums. So use the first input, and I'll use a resolution of 12 because, as you can see here in my camera view, my camera is quite close to my ocean, so I want to get a lot of resolution. I used a grid size of 200, the C23, the wind direction, the fetch 400, and the chop of 2, so I get more choppy or more sharp waves. The amplitude is 1, and I'm going to show you what the wave instancing does. So let's create a grid. Let me just 200 by 200, the resolution like 512. Sorry. Okay, it doesn't matter. And use a ocean evaluate, ocean spectrum, and the grid. Right now, if I, for example, increase this to 100, we get some, let me change this to flat shaded. Maybe it will be much, or let's increase the amplitude just for now. So you can actually see that there are circles of ocean that are being patched, and this controls how large are those instant oceans. So for example, if I put this just to 20, this point here, which you can see, instances 20 meters around. So I put this to 140. And also what happens if those points overlap, the ocean evaluate or the ocean spectrum will add more amplitude to the wave, which I'll also showcase because I used it, because I wanted more or bigger waves closer to my camera that there were in the distance. So let's copy this one. The second was the second ocean spectrum was a bit different. I used, wait, let me change the amplitude back to 1. Also, the second one was everything same here. I just changed the C to 8. The wind direction was still 15. This was 300, and this was 0.5. The amplitude was smaller, 0.45, and the wave instancing was 140. And yeah, that's it. Now we're gonna merge them back together. And we wanna, as you can see, we have all the attributes. Now we wanna split our ocean spectrum into low and high frequency. We can do that by using particle fluid mask. So by plugging in the right input, the ocean spectrum, and plugging the null into the left input. And we want this to be low, so we're going to filter above 7. And we want this to be high, so we'll filter above, not above, but below. And yeah, don't forget to place 7 in here. Let's add nulls. Use the right input or the second input, because this one is for the mask and this one is for the ocean spectrum. So low spectrum. Maybe let's color them like so, and this is going to be our high spectrum. Okay. So we're gonna work with the low for now. So we can maybe also use this one, create an ocean evaluate or evaluate. It's hard to pronounce. But we want to add more amplitude near. So the thing we can do is we can actually use a, so we're gonna merge in here because we're gonna add actually points to our grid, and we're gonna use a object merge. This object merge, we're going to retrieve our camera origin and place it in here. So now we have a camera origin, but we want it to be on the ground, like all other points. So we're gonna use a wrangle and say $p, or dollar. We're gonna say $p, yeah, equals 0. So now the point, if I can visualize it, is on the ground. We want to time shift this to be in this particular, in the first frame, because our camera is aiming downwards or down at the first frame. So also what I did use transforms because I just played with it. So I had actually 2 points. So transform, then merging them back. So this transform had 30.3. Let me actually make the points bigger so I can actually visualize them. And the second transform was 25 and 41. Now, if I add this and preview this again, maybe something like this could be good to see it. We get a higher amplitude of waves where the points are because it instances more of the spectrum there. So this was all I did here to actually add more detail. Okay, so we can save this to disk. So let's use a file cache. Call this low spectrum. It's not a simulation or time dependent, and I want it to be node name. Save to disk. And also for the high frequency, the same as before. And call this high spectrum. And save this to disk. So this is going to be the end for this lesson, and I'll see you in the next one. Welcome to our third lesson for this chapter. In this lesson, we'll create our simulation bounds. So we can start by placing a split because I want to split this to near and far ocean. So split this something like this. Let's place some nulls. Ocean near, ocean far. Okay. So since we actually haven't created our simulation, we don't have the bounds for our simulation, but I know it's going to be something like 77.5 for the 2.5, 67.5, 6.5, 19.5, and 6. Of course, if we when we create the simulation and we already we'll know the bounds, we're gonna copy the relative reference. So it's actually procedural and it actually changes its size based on our simulation bounds. But for now, this should be enough. you don't necessarily need to use a boolean, but I had issues when merging my simulation with my outer ocean. So I decided to use a boolean instead, since I'm going to compute it only once, and after that I don't really need to compute it again. But there's an issue. We get a geometry or mesh under it, which we don't want. So we're gonna set a wrangle, and we're gonna use a little bit of x. So if $p.y is smaller than, I don't know, 0.01, or let's set this to 5, then remove point based on from the first input based on its point number. Maybe let's set this to, oh sorry, it needs to be negative. Yeah, now it's working. But let's set this to 0.05 again. So yeah, we got rid of that. And also, just for safety, I'll add a clean node. Maybe there's some points. So also, this is not necessary, but I had issues also with merging it with the simulation, since the simulation has significantly more resolution than the grid here. I decided that I'll resample only the edge of the script so I can actually get more detail. So we can do that by creating another box, or we can actually copy reference this box here, based relative reference, add 5 to every direction, and also copy the position. The next step would be to actually create a volume out of this. So I think I used the value something out like this, and I created density. So now we can use a wrangle. This is going to be second input and our first. So we want to sample this volume and sample the values, or not sample the values, but if there is a value in the density, I want to set it to 1. And if there's not, it's going to be set to 0. So if a volume sample, we want to use the second input, and it's called density. I want to sample it on the position. And if this is smaller than 0.1, then set subdivide attribute to 1. We want this to be actually a float, because we will blur it after it, so we will get actually values ranging from 0 to 1. And also else, copy the same, but just set this to 0. Now we can set a color to visualize this. I'll use a red one. We're gonna use a attribute blur. And use a pretty high value here. So something like 50. As you can see, it blurred out. Also, it kind of I want to push this a bit outwards, so I'll use another wrangle. And here we're just saying we're just going to subdivide. Oh, did I write? Yeah. Subdivide equals dollar subdivide. Oh, sorry. Equals fitted subdivide from 0 to 0.5 to 0 to 1. So if you visualize this, it actually makes it more rough, if I say. Again, as we did up there, based on, or like when I promote this to primitives, since you can't actually use a subdivide based on a point attribute, so we need it to be a primitive attribute, and use a subdivide. Oh wait, we don't want to subdivide the entire geometry. That's just too much. So dollar subdivide is greater than 0.75. That was my actually final result, and I actually used a different algorithm. I used the open subdivide bilinear. So let's see what it creates. Actually, I'm not sure right now if it's not subdividing. Yeah, okay. It's subdividing everything except for our... Okay, so just turn this around. Yeah. So as you can see, now we have more resolution on the edge, which is quite unnecessary because it fixed the issue just a little bit, but it's not necessarily going to slow down the caching or the rendering. So I decided to do it anyway. And we can cache this out to the disk. So file cache, node name, simulate, not a simulation, time dependent, and let's call it ocean near static, and save this to disk. And this will be everything for this lesson. And next lesson we'll create all the necessary attributes for our oceaneer. Welcome to our fourth lesson. In this lesson, we'll prepare our oceaneer for rendering. So the first thing I want to do is I want to actually add our low frequency ocean spectrum. So I'm going to copy and paste the object merge, like so. And now we want to optimize this because we have a grid that represents the entire sequence. And the problem with Karma is that even if you set the outer this dicing, I'll show you. Or at least it didn't work in the previous versions. If you set the off-scene dicing to 0, and also you placed, I tried everything, it would still take ages to, or significantly more to dice the mesh. So a really cool or really good thing is to just remove everything that's not in the camera or the current frame. Thus, it's just going to displace the geometry that's actually seen in the camera. So we're going to use a volume for that, where we can get from camera. So we want a density to be value of 1. Let me visualize this. It's probably going to be black or white. Yeah, okay, it's white. That's good. And that's 550. We want to add, we want to make it much longer. And we want to add some bounce to it. Did it get actually dark again? Okay, I don't understand. I guess it depends on, I don't know, probably the shading or something. Want to set the bounce to minus 0.5, so we want to actually extend it. 0.1, and so on. Now we're going to use a wrangle. I want to actually sample this volume, so This is totally enough. I probably can use even more, less. 1500 should be enough, but let's use 1600 to be safe. The thing I'm gonna do here is I'm gonna use a if function, volume sample of our first or second input, the density volume, and sampling the position is is smaller than 0.01, then remove point from the first input based on point number. So now you can see it actually removes all the unnecessary geometry, and it will actually speed the rendering quite a bit. Now we can continue with creating additional attributes for our rendering. So I'll use few wrangles, or we can maybe do it in a single wrangle. I'm going to need a displace mask that's going to equal 1. This is going to be actually a float, and it's going to be a primitive attribute. So because later I'll use this attribute to displace only the areas in my simulation that are not part of the monster. The second one we want to get is the ocean ID, which again I'll use in the rendering to create masks and so on. The ocean is kind of simple because realistically those masks are used mainly in the simulation to mask everything else. And the reason why I need to use those masks here is because I decided to use the same shader for my simulation as for my ocean. So that's why we need these attributes. And they're details, so they're not slowing the simulation that much. Also, what we want to do is attribute promote our, attribute from primitive to point our distance attribute in here. And we're going to attribute blur it. So, oh no, sorry. We're gonna use a wrangle, and the reason why we need this attribute endpoints is because we want to use a wrangle where we create our ocean foam mask. Because in the final rendering, I'll have a area, for example, like 400 meters, that's going to be simulated, and the rest is just going to be a texture on the ocean. So this is why we need the mask. So we call this ocean foam mask and fit this from distance from 440 to 460 meters to 0 and 1. Let's visualize this. So you can see this is going to be the part without foam, and this is going to be the part with the displace or the foamed as a texture, not as a actual simulation. And also we want to create a ocean detail displace attribute, which I can create here. It's a detail attribute again. Ocean detail displace. The reason for this is because I didn't get enough detail from my ocean spectrum, so I actually added in the render my noise. I added noise on top of the ocean, which added little wrinkles and ripples to the ocean. So that's why I need this. Because again, I don't want to add those wrinkles to my water monster. And we can create a null. I could call this out out ocean near render. And also, I don't think we're going to need our subdivide attribute and also our distance attribute. So we can create a delete attribute. And distance and subdivide attribute. So this is going to be all for this lesson, and I'll see you in the next one. Welcome to our 5th lesson of this chapter, and in this lesson we'll prepare our ocean far for rendering. So let's take our grid. I want to delete the distance attribute, so delete attribute dist, and I want to ocean evaluate also the um, the low and the high frequency. The reason for that is because the ocean fire won't be resampled or won't be displaced, so it won't make a lot of difference actually to displace the high frequency, but it adds a bit more roughness to the geometry. So, yep, like so. The next thing we want to do is we want to create all the necessary attributes. So let's create a wrangle, and we want to run this on detail. So we want this to be a ocean ID that equals 1. Then we want to have a displace mask. So since this is not going to be displaced, we're going to set this to 0. And ocean foam, since we know the foam is going to be as a texture here, we want to set this to 1. So $ocean foam mask equals 1. And the ocean detail displace, we don't want to get since we're not actually displacing the mesh in the rendering, we actually want to set this to 0 because we don't want to add additional detail. So we should have all the necessary detail attributes. Oh wait, sorry, this should be 0. My bad. And oh, why did I write twice ocean ID? Let me check. Oh, this is supposed to be a displace mask. So we're not creating or we're not making any displacement in the rendering, so we're gonna set this to 0. And yeah, that's everything for our ocean far. So let's place a null and call this out ocean far. Yeah, and I'll see you in the next lesson where we'll going to add actual velocity for our velocity blur in rendering. Welcome to our 6th lesson, which is also going to be our last lesson for this chapter, and in this lesson we'll create our velocities for our velocity blur. So the first thing we want to get is the ocean velocity, so we can use the point velocity here, or get the point velocity. I can show you. I'm not going to enable the point velocity in our high frequency since it's pretty minimal and won't make much of a difference. The additional thing, or another thing which we need to add, in my case it's pretty important since my camera is pretty dynamic, is the camera's motion blur. So we can get that by using a function toNDC. So we want to convert this 3-dimensional data to normalized device coordinates of our camera. So position equals 2NDC. Here we want to put our camera. So it lives in OBJ and it's called render cam. And use the position. So and now we want to actually get the shutter open and shutter close. So we can use a time shift for that. Because afterwards we're going to subtract the positions and we're going to get a vector, which is going to represent our camera's motion blur. So plus 0, sorry, this is shutter open, so it should be subtracting. Disable integer frames, copy this, and add. So now we want to retrieve this position back to our geometry, so let's use a wrangle. first position is gonna, or the second input is gonna be the shutter open, and the third input is gonna be the shutter close. So, okay, so let's create a variable vector open position, and let's use a function point. We're gonna retrieve it from the second input. It's a position, and based on point number. Copy this. I'll actually say this, set this to manual for now because it'll be cooking and it's not really what we want. Set this to close and set this to the third input. So now I want to convert this data from the normalized device coordinates of our camera back to three-dimensional space. So let's create a, or let's copy this here. Oh, sorry, I said open with N. Yeah, let's try it now. Equals from NDC. I'm gonna copy our camera directory so I don't need to write it again. And instead, and we're gonna use this position here. And we're gonna do the same for the shutter close. So close, close. And now what we want to do is subtract open position from shutter from our closing shutter. So, and let's also add it directly to our velocity. So open, sorry, close, pause, minus open, pause. So let that cook. It cooked itself. And as you can see, if I disable enable, we're actually getting a vector which is pointing downwards, which is good because our camera is moving from looking down to looking horizontally. So that's exactly what we need. But the issue is with the magnitude of the length of the vector. And I'm going to show you why, because let's create a point. Let me see, yeah, good. And let's create a point, sorry. Okay. Point velocity. And add like 2. So this vector has now a magnitude of 2. If I would place this particle in a pop net with no actual or no other forces, just in its initial velocity of 2, this particle would reach a value of 2 in the x-axis in 24 frames. The reason why it's 24 frames is because our project is set to 24 frames per second. So the magnitude of the vector, or the length of the vector, also represents the speed in meters per second. So, but as you can see, we're subtracting actually just minus 0.25 and plus 0.25, which is half of a frame. But we have actually 24 frames, so we need to actually multiply it by 48. Since this is 0.5, we have 24 frames, and to get actually the right amount, we need to multiply it by the frame range, or by the FPS, and by 2. Since this is not actually a full frame, it's actually half of a frame. And now if we load it back, you can see that our velocity is significantly bigger, but now it has the right magnitude. And you can actually see that in my circumstance, it's pretty important to add the camera velocity because it's pretty big. So let's collapse this into a subnetwork. So since I'm gonna use this quite often, pretty much almost in every geometry I'm gonna be rendering, so let's call this camera velocity. Okay, so let's do the same for our ocean here. So let's set this to manual, copy this, paste it here, and retrieve the point velocity, and let's load it. As you can see, we're getting the velocities and everything is fine. So yeah, that's gonna be all for this lesson, and I'll see you in the next chapter where we're going to dive in the basic animation of our water monster. So see you there. Bye.